As you've probably figured out by now, we are working with some very small particles, and so that means they come in very large groups. We never see a single atom or just a couple of atoms at one time in chemistry. So it would be nice to have a really large unit for counting atoms that would be practical instead of counting them by ones or twos. Because they're so small and because they come in such large quantities, even a million or a billion or a trillion is too small of a number to use for practical purposes. So chemists have invented a new number that has a name. It's called the mole. This is a named number, sort of like a dozen. A dozen always means 12, and it doesn't matter what you're referring to, it's always 12 of that thing. 12 eggs, 12 donuts, 12 whatever. Well, a mole is like that too. It's a named number, but it's a way bigger number than a dozen. Let's take a look at what it is. The mole is defined as exactly the number of particles as there are atoms in exactly 12 grams of carbon-12. Now, we don't know how many atoms are in 12 grams of carbon-12 exactly, but we do have a pretty close estimate, and it's this: 6.022 times 10 to the 23rd is pretty close to the number of particles that would be in exactly 12 grams of carbon-12. This number has a name. It's called Avogadro's number, named after Amadeo Avogadro, who was an assistant to Galileo Galilei, who you might have heard of before, a much more famous scientist than Avogadro. So Avogadro's number, 6.022 times 10 to the 23rd, is a number like a dozen, except it's not exact, but it always refers to the same quantity. The atomic mass that you read on the periodic table, like when we read 1.008 for hydrogen, that's the mass in U's of one atom, but it's also the mass in grams of 1 mole. And that has to do with the fact that both the AMU, the atomic mass unit, and the mole are based on carbon-12. So that's not a coincidence. That was planned that way. So that those numbers on the periodic table have two meanings: the mass in U's of one atom or the mass in grams of 1 mole of atoms. We call that the molar mass. Mass of 1 mole is called molar mass. And it's useful for lots of different things in chemistry. You'll use this almost every day from here on out. So, for example, when you go back to hydrogen, that 1.0079, that's the mass in grams of 1 mole of hydrogen. It's also the mass in U's of 1 atom. So that's a dual purpose number. It means 1.0079 U's per single atom on average, but it also means 1.0079 grams per mole of atoms. Same thing with oxygen. The 15.999, that's U's per atom, and it's also grams per mole of atoms. Or for carbon, 1 atom has a mass of 12.011 U's. 1 mole has a mass of 12.011 grams. In the lab or in the field, when we practically measure things, we measure them in grams or something related to grams. But chemical change takes place atom by atom, or we can say mole by mole. So grams is a unit of mass that we use for weighing things, but moles or atoms is a unit of how things actually occur in nature chemically. So we need a way to convert back and forth between the two, and molar mass turns out to be the key to doing this. I'm going to teach you 3 different techniques that you can pick and choose from for converting between grams and moles and grams. The first one that I'm going to use is something that you're familiar with, and that's called proportions. On one side of the proportion, we put the molar mass. So for aluminum here, I have 26.982 grams per mole, grams per 1 mole. That's 1/2 of my proportion. On the other side of the equal sign, I solved my problem by putting the correct known and unknown in the right spots. So this question is asking how many moles of aluminum is 11.9 grams. Grams are in the top here, so I'm going to keep grams in the numerator on the other side of the equal sign, and I'll write 11.9 grams. And then my unknown is how many moles, x. I cross multiply and divide to get my answer, and x comes out to 0.441 moles. Grams have canceled. You try this one. How many moles of uranium is 15.64 grams? Stop the video and try it out. Okay, here's your answer. If you look up uranium on the periodic table, you find out that it's 238.03 grams per mole. So 15.64 grams is X moles. Cross multiply and divide, and you can find your answer. I should have 4 sig figs in my answer, and I get 0.06571 moles. Try this one. Now this is a little bit different because I'm not giving you mass, I'm asking for mass. Instead I'm giving you moles, but you should be able to do it. Pause the video, give it a try, I'll come back with an answer. Okay, I can set up my proportion this way. If I look up copper's molar mass, it's 63.546 grams per mole. On the other side of the equal sign, I'm going to put in the denominator 1.25 moles. And I'm putting moles in the denominator because that's where it is on the other side of the arrow. X is my unknown, that's how many grams are in 1.25 moles. I cross multiply and divide to find my answer. So it's 1.25 times 63.546 divided by 1, and to 3 significant figures that comes out to 79.4 grams. Another technique that you can use is dimensional analysis, which we have used before in here. This is actually the one I prefer because it's easier to use in setting up multi-step problems. Here's how it works. I start out by writing down the given information in my problem. In this problem, it's 0.385 moles, so I'll write it down. 0.385 moles of silver. And then I know that the question is asking me what mass, so that's grams. So over here I want grams of silver to show up in my answer. I just make the units work out right, and the arithmetic will automatically work out right. Molar mass is my key to converting. I'm going to put my 1 mole on the bottom so it cancels, and I'm going to put the grams on the top so that they don't cancel and they show up in my answer. Well, for silver, it's 107.87 grams per mole. With the mole canceled out, I will now get my answer, and to 3 significant figures, it's 41.5 grams. Here's how you can go the other way. How many moles is 13.6 grams of hydrogen? So I'll start out again by writing down what I've been given. 13.6 grams of hydrogen. Now I want my answer to end up with units of moles. So I'm going to put the molar mass in here upside down with the gram part on the bottom because I want that to cancel, and the 1 mole part on the top because I want that to be in my answer. So I look it up for hydrogen and I find 1.0079 grams per mole. Grams drop out. And what the problem is telling me to do is take 13.6 and divide by 1.0079. To 3 significant figures, my answer is 13.5 moles of hydrogen. You try one. What mass of titanium is 2.56 times 10 to the minus 3rd moles? Pause the video, try and work it out, and I'll come back with an answer. Well, here's how you can work this out. Again, start out in dimensional analysis by just writing down what they give you. 2.56 times 10 to the minus 3rd moles. What am I trying to get to? Well, I'm trying to get to grams of titanium from moles of titanium. How am I going to get there? Well, I want moles on the bottom so that it cancels out. So that's where my 1 mole part goes of my molar mass. I want grams in the top because grams are supposed to be in my answer. Now, if I look up titanium on the periodic table, I get 47.87 grams per mole. So now with my mole canceled out, I can do my arithmetic and find out how many grams are there. 0.123 to 3 significant figures is my mass. Try this one. How many moles are 15.56 grams of iron? Start out by writing down what you're given. 15.56 grams of iron. Include the target over to the right. I want to know how many moles of iron this is. What do I want to do for units? I want grams to cancel, so I put that on the bottom. I want moles in my answer, so I put that on the top. For iron, it's 55.847 grams per mole. Unit analysis, grams cancel, moles are in my answer, and that's what I want. I need 4 significant figures, and it comes out to 0.2786 moles of iron. Now there's a third technique. If you don't want to do dimensional analysis or you don't want to do proportions, you can always just remember this memory device here. And with these types of memory devices, you cover up what you're trying to find, and it tells you what to do with the remaining information. For example, if I cover up grams, this tells me to find grams, take moles and multiply by molar mass. If I wanted to find molar mass, I would take grams and divide by moles. If I needed to find moles, I would take grams and divide by molar mass. So that's another technique that you can use to convert from grams to moles. You can also use Avogadro's number in a similar way, but not for converting from grams to moles, but from converting back and forth between atoms and moles. Here's an example of what I'm talking about. How many atoms are there in 3.05 moles? I can set this up and solve it by proportions. I know that there are 6.022 times 10 to the 23rd atoms in 1 mole. That's the definition of a mole. On the right-hand side, then, I'm going to put my 3.05 moles on the bottom. Remember, you want to keep what's in the numerator for units in the numerator, and what's in the denominator for units you want to keep in the denominator. And my unknown is how many atoms, so I'll put x up there. Now I cross multiply and divide to find out what x is. So 3.05 times Avogadro's number comes out to 1.84 times 10 to the 24th atoms. I could solve that same problem using dimensional analysis. So I can go 3.05 moles and write down over here my target unit, which is how many atoms. And then the conversion factor that's going to help me is, here's 1 mole, and 6.022 times 10 to the 23rd is the number of atoms in 1 mole. Why is that useful? Because now moles cancel, and my unit is atoms. So then I know when I just multiply 3.05 by 6.022 times 10 to the 23rd, I'll have my right answer. And of course we saw it before, it's 1.84 times 10 to the 24th. So either proportions or dimensional analysis can help you convert between moles and atoms. And there's another memory device. If you want to know how many atoms, cover it up. It tells you moles times Avogadro's number will tell you atoms. If you want to know moles, well, it's atoms divided by Avogadro's number when you cover up moles. Okay, solve this one. Pick your method. How many atoms are in 1.92 times 10 to the minus 10th moles? I'm going to solve this using dimensional analysis. 1.92 times 10 to the minus 10th moles is what I'm given. My answer is supposed to be atoms. And the conversion factor that gets me from atoms to moles is Avogadro's number. So 6.022 times 10 to the 23rd atoms per 1 mole will cancel off the correct unit and give me the correct unit in my answer. I get 1.16 times 10 to the 14th atoms. Try this one. Stop the video, give it a try, watch my answer later. I'm going to use a proportion for this one. 6.022 times 10 to the 23rd atoms is the equivalent of 1 mole. So 2,500 atoms are going to go in the numerator, and my unknown number of moles is going to go in the denominator. When I cross multiply and divide, it's 2,500 times 1 divided by 6.022 times 10 to the 23rd, and I get 4.2 actually, times 10 to the negative 21 moles. How many moles are in 3 kilograms of carbon? Well, I'm going to set this one up in dimensional analysis, and here's why. Because it's a multi-step thing. I would have to do 2 proportions or convert kilograms into grams because I don't know how many kilograms are in a mole. So here's what I can do. I'll write down 3.0 kilograms, and my target unit over here is how many moles. My first step is I'm going to change this into grams. There are 1,000 grams in 1 kilogram. So this conversion factor will give me grams. Now I can put molar mass in here. This is carbon, so 12.011 grams per mole. I look this up on the periodic table. Grams now cancel, and ultimately I have the answer that I'm looking for, which is moles. To 2 significant figures, this comes out to 250 moles. Well, now you have a bunch of tools that you can use to convert between atoms, moles, and grams, and as we've seen by extension to kilograms and other mass units. This will be a very powerful technique that you will use repeatedly in the rest of this class.